Welcome to this executive session. Today, we are exploring one of the most critical frontiers in industrial operations, the intersection of artificial intelligence and human judgment. As AI increasingly monitors our machinery, a fundamental question emerges for every industrial leader: who actually makes the final maintenance decision? We'll be discussing a robust governance, safety, and operating model design specifically for the complexities of the 2026 industrial landscape. Let's start with a scenario many of you know well. It's 2:13 a.m. Your AI model is 84% confident that you should keep running for another 8 hours. But on the ground, a technician notices a slight vibration. What the model can't see is that a spare pump is currently unavailable and a bypass is in service. In this moment, the decision isn't a probability on a screen. It's an accountable act with real-world consequences for safety and production. The answer to our opening question is clear. AI informs, but humans decide, and governance defines exactly when and how that happens. Final authority should not be delegated just because we are enthusiastic about automation. It must move in lockstep with the severity of the consequences. The board's role is to set the boundaries, while the site's job is to make every decision visible and auditable. Why is this a board-level concern? Because a maintenance decision is, at its heart, an enterprise risk decision. A single recommendation affects safety, operational continuity, regulatory compliance, and capital efficiency. The moment a piece of technology influences physical action on an asset, it ceases to be just an IT project and becomes a matter of corporate governance. Maintenance has always been a system of judgment. AI is simply a new, powerful entry into an existing chain of sensing, interpreting, and acting. While AI can significantly accelerate how we detect patterns or interpret trends, the accountability for the final execution and the learning that follows still rests within our established control environment. To manage this effectively, we must maintain a strict distinction between three layers. AI provides the prediction, what is likely to happen. Humans then make the decision, what we should do based on risk tolerance and context. Finally, accountability defines who owns the outcome. A high-confidence prediction is useless if it leads to the wrong decision because the broader context was missing. In our first section, we'll look at capabilities, understanding what machines see versus what people know. The strongest decisions occur when we combine the scalable pattern recognition of AI with the consequence-aware judgment of a human expert. AI excels where patterns exceed human bandwidth. It doesn't get tired and can simultaneously monitor thousands of signals, looking for multivariate changes in vibration and temperature, recalling years of history, and surfacing weak signals long before they cross traditional alarm limits. It provides a level of consistent triage that no human team could match. Think of AI as a tool that turns fragmented history into operational memory. By linking sensor data, operator logs, and lab results, it builds a comprehensive context for every asset. However, this is only possible if our underlying data history is structured, linked, and genuinely trusted. But we must also acknowledge the blind spots. An AI model often operates with false confidence because it cannot see what isn't in the dataset, such as temporary bypasses, novel failure modes it hasn't been trained on, or the current availability of spare parts. These organizational realities are often where the highest risks reside. This is where human judgment becomes irreplaceable. Humans integrate consequence, context, and intent. We ask, what is different today, and who could be harmed? Competence isn't just intuition. It's the disciplined integration of incomplete evidence under an accountable authority. Of course, humans are fallible too. We suffer from fatigue, confirmation bias, and time pressure. The solution isn't to replace humans with unbounded automation, but rather to design an error-tolerant system where AI and humans complement each other to catch these predictable biases. Ultimately, the relationship is complementary, not competitive. AI should make expert review sharper by quantifying uncertainty and retrieving precedents, while experts make the use of AI safer by testing the plausibility of its recommendations against local context. Each side should challenge the other to reach a better decision. Moving to our second section, decision rights. The principle here is simple. Authority must follow consequence, not convenience. We can use automation aggressively for reversible work, but we must preserve human authority wherever an error could cause material harm. Not all decisions are created equal. We classify them by their reversibility. Some actions are observe only, where AI just flags an anomaly. Others move toward recommend or authorize, and finally act, where the AI might change an equipment state directly. Each level requires increasing degrees of safeguards. We use a 5-level autonomy ladder to manage this. We only move up the ladder when the evidence is overwhelming and the safeguards are ironclad. Higher autonomy demands stronger validation and a faster, more reliable fallback plan if things go wrong. There are governance red lines where humans must always have the final say. These include safety-critical barriers, pressure boundary integrity, and environmental permit risks. AI can inform these high-stakes decisions, but it should never be the sole authority when we are operating near these boundaries. On the flip side, we should give AI room to act in green lanes, tasks that are bounded and reversible. This includes auto-triaging alerts, drafting work notifications, or monitoring for model drift. Our design principle is to automate administrative burdens first and asset state changes last. A decision rights matrix helps make this authority explicit. Depending on the consequence of failure and how easy it is to reverse an action, the system defines whether the AI merely recommends, a human must approve, or a named authority must have the final word. The same model might have different rights on different assets. We also need clear escalation triggers. If data is missing, the model shows drift, or the plant is in an abnormal state like a startup, the system should automatically freeze automation, expose all evidence, and route the decision to a named human authority. Crucially, human stop-work authority remains absolute and must be frictionless. No AI score or schedule should ever override a person's credible safety concern. Overrides should be reviewed for learning, never punished, to ensure we don't discourage safety-conscious dissent. In Section 3, we focus on the operating system. Our goal is to make every decision reproducible, not just explainable. A trustworthy system links data quality directly to the work control and outcome learning phases. This closed-loop architecture ensures that every AI recommendation lands inside a controlled maintenance workflow. From sensing data to executing the repair and finally retraining the model based on what was actually found, the audit trail remains unbroken. Data integrity is our first gate. In maintenance, garbage isn't just an IT problem, it's a safety hazard. We verify identity, timestamps, and quality before recommendation is even generated. If this gate fails, the system must degrade to human review rather than fabricating a false sense of certainty. When a recommendation is made, it needs to come with an evidence package. Instead of just showing a red light, the system should explain what changed, why it matters, how sure it is, and what the consequences are. This allows a human to inspect the basis of a decision in less than 2 minutes. We must never substitute confidence for consequence. As this matrix shows, even if a model is highly confident, if the consequence is high, a named human authority must remain the final decision maker. Consequence always dominates at the boundary. Human review should be a structured challenge, not a ceremonial rubber stamp. We use checklists to force reviewers to ask, what evidence contradicts this? And what is the worst case if we are wrong? We measure success by the quality of the challenge, not the speed of the click. For high-consequence decisions, we bring in multiple lenses: operations, maintenance, reliability, and safety. Because the AI has already prepared the evidence, these meetings can be short, focused, and decisive, led by a clear decision owner. We record every decision as if it will be read during an incident review. This decision log captures the evidence used, the assumptions made, and the residual risks. This isn't bureaucracy. It's the foundation of a defensible, learning organization. Finally, every outcome must be captured, whether we found a defect or confirmed a false alarm. That data must feed back into the system. Capturing no defect found is just as important for model retraining as confirming a failure. In Section 4, we examine failure modes. The partnership between AI and humans can fail in very predictable ways, and we must design controls to mitigate risks like automation bias, data gaps, and the erosion of workforce skills. The most dangerous failure is agreement without thought, automation bias. To combat this, we might randomly audit approvals, require users to cite contradicting evidence, or even hide the AI's answer until the human has made their own initial assessment. We also have to balance false positives against false negatives. An unnecessary repair has a cost, but an unplanned failure has a much higher risk profile. We optimize our models for risk-weighted error rather than just generic accuracy. Models can drift, even if the code doesn't change, simply because the plant environment changes, new fuels, different seasons, or equipment modifications. We treat every major configuration change as a model assurance event that requires revalidation. Missing data can be particularly insidious because it can look like normal operation. Our rule is simple. If there is no data quality status, there can be no autonomous action. Absence of evidence must be made visible and handled conservatively. AI also introduces new cybersecurity risks. We must protect the entire pipeline, from the field sensors to the AI service itself, ensuring that we can always fall back to a safe state, even if the AI network is compromised. There's also a human risk, that killing. If we remove the need for thinking, we eventually lose competence. Well-designed systems use AI to give experts more time for field verification and critical thinking, rather than creating a blind dependence on the screen. Section 5 covers governance. Governance is the gearing that connects the board's risk appetite to every single AI-influenced action on the shop floor. It makes accountability executable. We use the 3 lines of defense model. The first line owns and operates the system. The second line sets the policies and provides assurance. And the third line provides independent audits. This structure ensures that ownership and challenge remain distinct. Accountability must be clear before the model goes live. Using a RACI matrix, we name exactly who is responsible for model validation, who has the final say in high-risk scenarios, and who is informed of overrides. Ambiguity at 2 a.m. is a failure of leadership. We don't need to reinvent the wheel for AI governance. We can connect it to existing frameworks like ISO 55001 for asset management, NIST for cybersecurity, and emerging regulations like the EU AI Act. This ensures AI doesn't become an exception to our safety standards. Assurance is a stack that starts with data and ends with governance. Every layer must remain effective throughout the life cycle of the asset, from the sensors on the machine to the independent protection systems that act as a final safety net. To manage this, we measure decision quality, not just model accuracy. Are we avoiding failures? Is human review quality high? Are we seeing too many high-risk overrides? These balanced indicators tell us if the system is truly trusted and useful. At the board level, oversight should focus on 5 key questions regarding exposure, control, and learning. This dashboard keeps the focus on whether AI is improving our risk profile or inadvertently expanding it. Finally, let's talk about implementation. The strategy is to start narrow, prove control, and then scale deliberately. Trust is earned through consistent outcomes and transparent evidence, not through rapid, unvetted rollouts. A 90-day pilot should focus on proving the decision system, not just the math. We start by mapping the decision process and shadowing experts before going live with human approval and controlled monitoring. Scaling happens through reusable controls. Once we've proven a use case, we standardize the evidence templates and RACI models across the enterprise. We only promote autonomy after we have seen stable outcomes and effective human overrides. Let's look at a quick case exercise. A critical pump shows an anomaly. The model says it will fail in 14 to 30 days, but the field technician says things look stable. There is no standby pump available. This is a classic conflict requiring a nuanced decision. A disciplined decision here isn't just stop or go. It's a conditional plan. Reduce the load, conduct an independent review, and set explicit triggers for an immediate stop if conditions change. This is the integration of AI data with human risk management. When you return to your organizations next week, I suggest asking management these 5 questions. They will reveal whether your AI-assisted maintenance is truly governed or merely deployed. It's about ensuring the boundaries between human and machine are clearly encoded. In conclusion, let AI widen your field of view, let humans own the choice, and let governance make the boundaries unmistakable. Our commitment is simple. No material maintenance decision should be made without competent authority and a clear learning loop. This framework is built on a foundation of international standards and official sources ranging from NIST and ISO to OSHA. These references provide the legal and technical backbone for the governance model we've discussed today. Finally, please note that all content and visuals in this presentation are original and designed to provide a governance framework. Actual maintenance decisions must always follow your site-specific engineering procedures and regulatory requirements. Thank you for your time.